5.2 is solving systems of equations by substitution. In 5.1, we solved systems by graphing. We've taken a system of equations, a few lines, graph them, see where they cross, find their point of intersection. Today we're going to do a similar thing, but not by graphing, by a process called substitution. With substitution, you try to get a variable by itself. You look at the system, and you see which variable can I isolate the easiest. And out of these four options, this is the one that I can get by itself the fastest and the easiest, because it has a coefficient of 1. If you can find a variable with a coefficient of 1 or negative 1, get that variable by itself. So I'm going to solve for this x. So I have x plus 3y equals 10. I just took this equation down here. I'm going to subtract the 3y from both sides, and I get x equals negative 3y plus 10. This x is now by itself. I will take this, I'll take what x is equal to, plug it in for the other x. It has to go into the other equation. So now I have 2 times negative 3y plus 10 minus 5y equals negative 13. Excuse me. Move this all over here. Oof. This x right here got replaced by what x was equal to. X was equal to negative 3y plus 10, so I took this x and made it negative 3y plus 10. Now I have an equation that only has one variable. It has y a couple times. So I distribute and I solve. So negative 6y minus 5y, I put these two together, I get negative 11y plus 20 equals negative 13. I subtract 20 from both sides, and I get that negative 11y equals negative 33. Divide both sides by negative 11, and y equals 3. So I found y. The y value is 3. I now have to go back and find x. Well, this can be pretty simple. I just take what y is equal to and plug it in for one of my y's somewhere. So x equals negative 3y, and y is now 3. X equals 1. My solution is the point 3, 1. Point 31 works in both of these equations. And I could check that fairly simply. Just plug 3 in for x and 1 in for y. I get 3 plus 3 equals 6. Oh, I have it backwards. It's the point 1, 3, not 3, 1. X is 1, y is 3. The computer is being weird. Excuse me. If I plug 1 in for x and 3 in for y, I get 1 plus 9 equals 10. If I do that down here, I get 2 minus 15 is negative 13, so that checks. I'll do another example over here. This time, I don't have a variable that I can isolate quite as easily. None of these variables have a coefficient of 1, unfortunately. None of them are already by themselves. So I have to look at this and think which variable would be the easiest for me to get by itself. And if you want to pause and think about that for a second, it's a question worth answering. Which variable is the easiest one to get by itself? People often think, oh, I should just do the top right x. But that's not going to be very simple. What I want to do is this negative 2y right here. Because the coefficient negative 2 can go into 6, and it can go into 26. So when I get this y by itself, I won't have any fractions. That's the key. I'm trying to avoid having fractions. If I were to get any other variable by itself, I would get a fraction. Divide everything by 6, I get fractions here. Divide by 3, I get fractions here. Divide by negative 2, I get fractions here. All of those give me fractions, which I don't want, so I'm going to get the negative 2y on the bottom by itself. That gives me y equals 3x minus 13. Now that y is by itself, I'm going to take it and plug it in to the other y. So I get 3x minus 2 times 3x minus 13 equals 11. I plugged into that y up there on top. Do some simplifying. 3x minus 6x plus 26 equals 11. I just distributed the negative 2. 3x minus 6x is negative 3x. Subtract 26 from both sides. Negative 3x equals negative 15. Which means that x equals positive 5. Now that I know what x is, I can take that and plug it back into my box up here. That's what's really nice about this sort of boxing system that I use, is you can always tell where to plug things in really quickly. I'm going to save myself some space, though. So I'm going to have y equals 3 times 5 minus 13. So y equals 2. My solution is the point 5, 2. And I can check that. 30 minus 4 equals 26. That checks. I plugged in a 5 and a 2. 15 minus 4 equals 11. That checks also. So here's my solution. It checks. Sometimes you'll get equations that are already in like slope-intercept form, which means a variable is already solved for. In fact, in this top left one, both y's are already isolated. So I can just take one of them, plug it in for the other. So I get 3x minus 3 equals 3x minus 1. When I solve this, I'll subtract 3x from both sides to get the variables on the same side. Excuse me. 3x minus 3x is 0, so this becomes 0, and this becomes 0. We get negative 3 equals negative 1. This is not a true statement. Negative 3 does not equal negative 1. Whenever you have a non-true statement with no variables, when the variables have been eliminated, this is called no solutions. You can also just write it this way. This cannot be solved, because if you think about these two lines, they are parallel. They have the same slope, but a different y-intercept. They're never going to cross. They're parallel lines, so they have no solution. If you ever get something like 3 equals 2, or 1 equals 6, or 0 equals 1, these are all no solutions because they're not true statements without a variable. And top right over here, I'll get this x by itself, so I'll subtract a y from both sides. I get x equals negative y plus 4. I will take this and plug it into the other x. It always has to be into the other x. I get 2y plus, 2y minus 8 minus 2y equals negative 8. These two y's cancel each other, become 0, so you get negative 8 equals negative 8. This is a true statement with no variables. If you get negative 8 equals negative 8, or something like 3 equals 3, or 0 equals 0, this is infinite solutions. This is the same line, twice. One line is the same as the other. So there's no solutions and infinite solutions, how they can come up when solving by substitution. Finally, we'll do a little word problem. Nice, simple, silly little one. You have a piggy bank with quarters and dimes. You know there are 63 coins total in the bank, and the value of the coins is $11.25. How many of each coin are in the bank? We're going to do a lot of word problems with this chapter. We'll discuss a lot how to go about them, but the first thing you should always do is to define your variables. Meaning, what are you trying to find? So in this case, x will stand for number of quarters, and y will stand for number of dimes. Because those are the two things that we're trying to find. Then I'll make equations. I know that there are 63 coins total. So this is number of quarters plus number of dimes equals total number of coins. This is my number of coins equation. And I also know it's 25 cents per quarter, and it's 10 cents per dime, and altogether that's going to get me $11.25. This was money per quarter, money per dime, total money. This I can solve by substitution. If I want to get one of the variables by itself, I'll get this x by itself. So we get x equals negative y plus 63 if I subtract a y from both sides. I will now take this and plug it in for this x here. If you don't like having the decimals, you could multiply everything by 100 to get 25x plus 10y equals 1,125. It just moves decimals around, doesn't really help you all that much. I'm not going to bother, but you can if you'd like to. 0.25 times negative y plus 63 plus 0.1y equals 11.25. Distribute the quarter, so I get negative 0.25y plus 63 times 0.25. $15.75. Does that make sense? Yes, it does. Negative 0.25y plus 0.1y is going to be negative 0.15y. I'll subtract 15.75 from both sides, and I get that negative 0.15y equals 450, negative 4.5, and I will do negative 4.5 divided by 1.5, or 0.15, excuse me, and that comes up to 30. And this means there are 30 dimes. If there are 30 dimes, I can plug that back in up here. I know there must be 33 nickels, or excuse me, quarters. Because there are 63 coins total. Thank you. Hope you have a nice day.